measurements by Ulysses and the Stereo spacecraft, tell you about a new dust instrumentation, in fact the world dust telescope that it was invented by my colleague Eberhard Grün, and how to do this right, possibly on the lunar surface, addressing other outstanding issues about dust on the lunar surface at the same time. This is the trajectory of Ulysses. It was launched somewhat delayed than originally planned in 1990. It happened to be that when it encountered Jupiter and made a south turn, its orbital plane, it's nearly perpendicular to the incoming interstellar gas and dust, which is make it extremely suitable to make dust measurements and incredible discoveries. For example, interstellar dust flowing through the solar system. In fact, the dust was recognized because of its very high speed and also its directionality closely related to the flow of interstellar gas through the solar system. Immediately, that gives us an amazing idea that how to distinguish interstellar from interplanetary dust. Its directionality would be a dead giveaway, and it's also its speed. And of course, if it happens that you could do these measurements at Earth or on the surface of the moon, half the year you are flowing into the direction of the interstellar gas, interstellar dust. Half the year you are flowing against it. So there is a tremendous velocity modulations of 30 plus minus 26 as the interstellar dust would arrive. This animation actually just shows the trajectory of the Ulysses. This black or red dot is Ulysses. And what you have seen is the modulation of tiny particles. These are typically 0.3 or so submicron grains, 0.3 micron radius grains, that their trajectory is strongly influenced by the heliospheric magnetic fields. So one tries to build a model to the best of our ability to put down the history of the solar wind, how it carries out the Parker spirals, how these dust particles traverse through the solar system, but it is hard because they actually take about 20 years to get from 100 AU down to 1 AU, where these measurements are made. So we need the long-term, large-scale history of the magnetic field structure of the entire heliosphere. Modeling started early. This is from our colleague Markus Landgraf. Early on, he could measure and at least notice that as a function of time from 94 to 2005 at the time, there is a dip in the flux. That is clearly a sign of this interaction. The excess of tiny grains to the interior of the solar wind depends on what the sun is doing. Also, you could make a map or a history of the directionality of these grains are coming from. This complicated red line actually happens to be a single fixed point in the sky. That's where the gas and the dust is coming from, as seen on board the Ulysses. Because Ulysses is turning, it's making its orbit, so if you want to keep looking at the same direction, the rotation angle, the angle that direction appears to be measured from the ecliptical north, has a complicated history. And most of the time, the dust arrives from that direction, but there are significant deviation. Again, it's a signature of interaction with the heliospheric magnetic fields. And we do our best with our models. They are not perfect. There is another set of measurements recently, of course, is on stereo. This is, as of yesterday, the two stereo spacecraft, A and B. They are there to monitor the sun, help us protect assets in orbit, duck when big solar events are coming towards the Earth. But they also noticed something interesting. They claim it's dust, perhaps nanodust. This is a flux in some strange units as a function of time of events that appear to be dust impacts. Dust impacts by small grains that are coming extremely fast, 400 kilometers per second, close to solar wind speed. This is actually just 2 years. This is 2007 and 2009 from my colleague Dave Malaspina in strange units. This circle, the size of this circle represents 50,000 hits a day versus 400,000 hits a day as a function of time along the orbit. If you want to model this, it's hard, but we could try. Again, you need a good model of the heliospheric magnetic fields close to the sun, as these particles are generated very likely within 10 solar radii from the sun. I show you the density distributions and the velocities, and we could try to start comparing the measurements with the models. At the end of the day, what we really need is to understand the magnetic field structure in the heliosphere. This is as a function of time and latitude. the radial component of the magnetic field on the surface of the sun, whether it's inward pointing or outward pointing. That's the footprint that the solar wind will carry away and organize it in the large-scale heliospheric magnetic fields. That's the same as ballerina skirt of the heliospheric current sheet. Above this warped surface, everything is outward pointing, the magnetic field. Below it is inward pointing. This thing is spinning. It's beautiful. It's incredibly complicated. If you happen to be on Earth, if you make dust measurements, you would actually illuminate the region of space from the sun to you. If you make measurements of interstellar dust, you would illuminate the regions from 100 AU down to where you are. The dust is a tracer what the large-scale structure of the magnetic fields are doing. How can you do this measurement? Here it is. For example, you could use what we call a trajectory sensor, a set of wires arranged in 4 different planes. And when the charged dust particle will come through, it will generate the largest signal. Between the wires, the 2 sets of wires, it flies through. We could learn how to read that signal and read out the velocity and the charge of the dust particles. You could do more. You could actually, at the end of the day, or behind, or right after the trajectory sensor, you could build an impact plasma detector. You could measure the mass, and if you arrange it in a time-of-flight system, you could analyze the composition, the makeup of the dust particles. You could build instruments that have mass resolution over 200. I draw your attention to the silver lines of 107 and 109 that is widely separated in a laboratory experiments. You could get to the chemical and isotopic composition of interplanetary and interstellar material. What would you give for a piece of grain you know it's coming from another outside the solar system? Here is a dust telescope put together by your German colleagues. This is the trajectory sensor at the beginning, the impact dust detector at the bottom, with a time-of-flight system to give you all the goodies: mass, charge, chemical, and isotopic composition, with the knowledge whether this grain was interplanetary or interstellar. If you were to put this on the lunar surface, many of you would immediately remember the LEAM experiment. It had somewhat overlapping science goals: lunar ejecta and meteorite experiment, Apollo 17. And in a talk or two, Professor O'Brien will tell you whether these signals might or might not be real, but the suggestion is there's a lot of confusion about possibly slow-moving, highly charged particles. So imagine that we do something else to this dust telescope. The dust particle comes in, we measure its trajectory, then we put through a region with an electric field, a couple kilovolts of electric field, kilovolts per meter electric field. So the trajectory is bent, hence we immediately get to its charge to mass ratio. I will not be able to tell you its composition, but we have plenty of samples because the impacts are low energy. These particles are coming meters per sec. They will not generate a plasma cloud. But I will tell you the mass, I will tell you the charge to mass ratio, hence you have the mass and the charge for slow-moving dust, and you could get to the bottom of the LEAM confusion from the Apollo era. So actually, I am about done. Let me just list the type of people who might be interested to do this dust measurement on the lunar surface. If you are a heliospheric physicist, you would certainly like to know the large-scale structure and history of the magnetic fields. Closer to the sun than Earth and further out. If you are into astrophysics, you must be getting excited that we could with certainty tell you the chemical and isotopic composition, flux, and size distribution of interstellar dust with a clear way to identify they are really interstellar. If you are a planetary scientist, you could do the same thing for dust particles from within the solar system, and even having the trajectory information, identify whether they are cometary or asteroidal in origin. If you do this measurement precisely enough, maybe even identify the source, which parent body those particles are from. If you are a lunar scientist or a mission planner or anyone else, just most of this crowd here would like to return to the moon, this instrument would give you an opportunity to redo LEAM the right way, to deliver all its original science, plus this newly discovered possible effect of soil movement on the lunar surface. Thank you.
Yes, we have a... Thank you for being on time. Yeah? This is very interesting. I just wanted to add that in heliospheric physics, one of the issues that we've struggled with is understanding how solar wind implants itself within grains and is re-emitted. And it seems like, doing studies of dust and the composition of dust on the lunar surface would be sort of an ideal laboratory for this, because you have both known composition or relatively known composition associated with the lunar surface, and then the ability to differentiate composition of particularly the smaller grains, which then could inform exactly how those implantation processes work and re-emission processes work, which has been a really big and growing puzzle in heliospheric physics.
I couldn't agree more. My only comment, of course, this instrument alone is wonderful. If we could get our colleagues on board to do simultaneous fields and plasma measurements, then the value of the setup is exponentially higher.
But you need pickup lines.
I'm with you. Yes.
Any other questions?
You've described chemical composition there, really mostly in the sense of elemental composition. Is there any way to slow down a dust particle enough that you can actually look at its chemical reactivity? In other words, not just what elements are there, but what oxidation state are they, and so on, without the impact plasma, without the particle being destroyed?
Not to my knowledge. My colleagues might have a different opinion. But at some point, of course, the other extreme of this setup, instead of in situ chemical analysis and immediate analysis, of course, we have the sample return option. And it is possible to combine this instrument, for example, with an aerogel collector at the backside, and think of opportunities to end up with a long enough surface area times time to have significant exposure. And then when you decide you had enough, maybe find your way back to Earth and deliver the samples.
Thank you.
Any other questions? We have time for one more. All right. Thank you, Mihan.